Every CFD simulation you have ever run, every velocity field, every pressure contour, every drag coefficient comes from just three laws: conservation of mass, conservation of momentum, conservation of energy. Three principles that govern all fluid motion in the universe. In 9 minutes, you will understand what these laws say, how they become the equations your solver actually solves, and what happens when they are violated. Later, I will show you why one of these equations is optional, and when leaving it out gives you wrong answers. Conservation means a quantity cannot be created or destroyed, only transported. In CFD, we apply this principle to a small region of space called the control volume. Whatever enters through the surfaces must either leave through the surfaces accumulate inside, or be produced by a source. This is the finite volume method, and it is the foundation of almost every commercial CFD solver. We divide the domain into thousands or millions of small control volumes, cells. For each cell, we write conservation equations. Mass in equals mass out. Momentum in equals momentum out plus forces. Energy in equals energy out plus heat and work. Every cell must satisfy these balances simultaneously. The simplest conservation law: mass cannot be created or destroyed. The continuity equation says the rate of change of density plus the net mass flux through surfaces equals zero. For compressible flows, density varies with pressure and temperature. For incompressible flows, density is constant, and the equation simplifies to divergence of velocity equals zero. The velocity field must be divergence free. If fluid converges from one direction, it must expand in another. If your simulation shows mass imbalance, even half a percent, something is fundamentally wrong. Fix mass balance before looking at anything else. Newton's second law applied to a fluid element. The left side is the material derivative of velocity, how fast a fluid parcel accelerates. The right side is the sum of forces. Pressure gradient, fluid flows from high to low pressure. Viscous stress, friction between layers, proportional to strain rate for Newtonian fluids. Body forces, gravity, three equations for three velocity components. Combined with continuity, four equations for four unknowns, three velocities and pressure. This is the Navier-Stokes momentum equation, the heart of CFD. The first law of thermodynamics for a fluid: energy changes due to pressure work, heat conduction, and viscous dissipation. The key point: for isothermal incompressible flows, the energy equation is not needed. Mass plus momentum give four equations for four unknowns. Energy decouples. But the moment you have temperature differences, buoyancy, or compressibility, energy couples back in. Density depends on temperature. Temperature depends on velocity. Velocity depends on density. All three conservation laws must be solved together. There are two ways to write these equations: conservative and non conservative form. Conservative form writes fluxes as divergences. The finite volume method integrates these divergences over each cell, converting them to surface fluxes via the divergence theorem. What enters one cell face is exactly what leaves the neighboring cell face. No mass or momentum is lost in translation. Non-conservative form uses the material derivative, mathematical equivalent for smooth flows, but at discontinuities, shocks, contact surfaces. The non-conservative form can produce wrong shock speeds and incorrect jump conditions. For CFD, always use the conservative form. It guarantees that the discrete equations respect the same conservation principles as the continuous ones. The finite volume method turns conservation laws into solvable equations. Divide the domain into cells. Integrate each conservation equation over every cell. Apply the divergence theorem. Volume integrals become surface integrals over cell faces. Approximate those surface integrals using neighbor values. This gives algebraic equations, one per cell per variable. For a million cell mesh with four variables, 4 million equations. The solver iterates until residuals drop below threshold. When they do, every cell satisfies conservation simultaneously. That is convergence. There is a subtle problem. For incompressible flow, Density is constant. There is no equation of state linking pressure to density. Pressure appears in the momentum equations, but there is no explicit equation for it. This is the pressure velocity coupling problem. The solution is the simple algorithm, semi-implicit method for pressure-linked equations. It guesses a pressure field, solves the momentum equations to get velocities, derives a pressure correction from the continuity equation, updates both pressure and velocity, and repeats. Each iteration brings the solution closer to satisfying all conservation laws simultaneously. Simplic, PISO, and coupled solvers are variations that trade convergence speed for stability. But the fundamental idea is the same: use continuity to correct pressure. When your solver says converge, it means the residuals, the imbalance in every conservation equation at every cell, have dropped below your tolerance. A residual of 10 to the minus 4 means the error in each equation is 1/10,000th of the reference scale. But low residuals alone do not guarantee accuracy. You also need grid independence. Does the answer change when you refine the mesh? Mass balance. Is the global mass imbalance below 0.5%? And monitor convergence. Have the quantities you care about, like drag or pressure drop, stop changing. Convergence without validation is just precise nonsense. A common question: do you need the energy equation? For isothermal incompressible flow, water through a pipe at constant temperature, air over a car at low speed, no. Mass and momentum are sufficient, but you need energy when temperature matters. Natural convection, hot air rising, density depends on temperature through the Boussinesq approximation. Compressible flow, density depends on pressure and temperature through the equation of state. Conjugate heat transfer, heat flowing from a solid into a fluid. Combustion, chemical reactions releasing energy. The rule is simple. If your flow changes temperature, include the energy equation. If temperature is uniform, leave it out and save computational cost. Let me show you how this works in practice. Consider flow through a pipe bend. At the inlet, mass enters at a known velocity. The continuity equation ensures every cell conserves mass. No fluid appears or disappears. The momentum equations track forces. Pressure pushes the fluid around the bend while viscous stress slows it near the walls. The result is a secondary flow pattern, Dean vortices, that redistributes velocity across the pipe cross section. If the fluid is hot on one side and cold on the other, the energy equation tracks how turbulent mixing and conduction redistribute that temperature. All three conservation laws working together in every cell, at every iteration, giving you the velocity, pressure, and temperature field that satisfies all of physics simultaneously. Three conservation laws. Mass, nothing is created or destroyed. Momentum, Newton's second law for fluids. Energy, the first law of thermodynamics. The finite volume method turns them into equations your computer can solve. Every converged simulation satisfies all three simultaneously. Understand these laws, and you understand what your solver is actually doing. If this helped, subscribe for more CFD fundamentals every week.